So some background on projectile motion is, Galileo's first theorem is, projectile which is carried by uniform horizontal motion compounded with natural accelerated vertical motion describes a path which is semi-parabolic. That describes Galileo's first theorem on projectile motion.
Velocity of a paintball hitting a surface. And to do that, we're going to use these top two equations right here, the change in x equation, and then the final y position equation. For the change in x equation, we need change in x, the velocity in the x direction, and the change in time. We already know the change in time, and we know the change in x position, so we just need to find the velocity in the x direction.
And then also we know, we're going to figure out, we know the gravity. We're going to figure out the time by dropping a paintball when we shoot it to see when it hits the ground, because we know that x and y directions have no relation. And then so we'll figure out, we'll know what the y initial is because we're going to vary it by the rule of 10. So start from 10 meters all the way up to 1 meter. And then we'll figure out, and then we know what the initial y is. The velocity of the initial y is going to be nothing. So then we just calculate the equation. Once we find the initial y, we can find then the velocity of x, because we know the change in x position, because we know when it hits the base of the object, or when it hits the ground. So yeah. First, what we did was to figure out what the velocity of the paintball is shooting. We set up a board and started at 0.10 meters. 0.10 meters, and we trying to figure out how fast, find out how many seconds it was until the bottom of the board. So what we did was we took the ball and dropped a paintball at the exact same point, because we know that x velocity and y velocity are different. So then we know that when the ball drops, two balls are going to drop at the exact same point and hit the ground at the same point. So what we figured out that was 0.14 seconds, around 0.14 seconds, and we went through the entire equation and figured out that the velocity was 85.63 meters per second that the paintball shot.
To find velocity, we use the change of position equals the velocity times change of time equation. And change of velocity equals change of position over change of time. And we use 12.18 meters for change of position and 0.1428 seconds for change of time. And we put these values in and got after putting the values in, we calculated and got velocity equals 85.36 meters over seconds.
We've measured already. We've measured 0.10 meters. 0.10 meters. All right, it's level, it's flat. We leveled it. Now we're firing. It looks like it just dropped. So we're going to count out the feet. Michael's coming to measure how far it was where we shot. How far is it?
All right, this is 41 feet.
41 feet, all right.
For trial one, we use the YF equals 1/2 gravity times time squared plus the initial y. And we got we got 1.02 equals time squared time equals 0.1428. As we found time, we plug this in over here and got and after calculating this, we got change of position equals 12.18 meters. And that's the right answer.
And we actually, when we calculated it outside, we got 12.8 meters. So we're off by a couple of tenths of a meter.
1 meter now. Paintball guns level.
Y final is 0. 1/2 gravity, and gravity is -10, is -5. T squared plus, since we started this subtracting, we did 1 meter. Subtract that, that's -1 equals -5 square root of t. Divide that by -5. That is 0.2 t squared. Square root, take the square root of each one. So then t is equal to 0.4517. Plug t into that equation. Then 0.45 minus 0, you get triangle t. Our velocity of x is 85.36 meters. And times the velocity times this by that, and you get, so then you get 38.56 meters is what that was when we shot paintball for 1 meter. We got 38.1 meters, so we're off by a little. 0.7 meters level firing.
Trial 7 used the same exact equation, but initial y is now 0.7. First call this over, I will be 0.7 over, and that will give me 1.4 equals t squared. Square root that. T equal 0.379. Put this in this equation. Change of position equals and we got 32.25 meters as the same position, and the error of margin is 0.25 meters.
All right, so this is our converted graph of our y, our y time graph of meters. And so what we do is we square the seconds, which is x, and we have our regular y meters, which gives us our linear looking graph. And then here is our non-linear, our normal data of our expected data should be not our actual data, of our expected data. And that's what it looks like. And again, this is what our normal data looks like. Great.
All right, this is our data. There are different trials. These are distances, our actual distances, not the expected ones that we talked about. Those are our times that we calculated, and our velocity was constant from the velocity we calculated during the drop experiment. This is our graph of our actual in time, 0.1, 0.2, 0.3, in distance in meters, our mathematical model, and our statement. What it should be is it should show exponentially increasing, be due to gravity and accelerating, but because we're using such small numbers that it's not going to show that.
Alright, so we're going to talk about the errors that occurred in our experiment. So overall our distances were different from what we expected our values to be, mainly because of the line of sight that we chose was not necessarily perfectly horizontal. The gun did not shoot every time at a constant velocity, so the velocity wasn't the same every time that we shot, and the gun itself made the ball spin in different ways, mainly in a backspin rotation. So that's why our experiment did not turn out to be perfectly the correct way.